Welcome to Chemistry Solutions with Steve. This is an AQA GCSE Chemistry Higher Tier Paper 2 walkthrough, and it's the June 2024 paper. You can download this paper from the AQA website and you can work through it however you wish. You can put it onto your computer or laptop. Do one question at a time, pause, mark it. You can print it off and use it as a mock exam. The choice is yours. Before the exam, you'll be directed to look at the front page. Note how long the exam is. Check you're in the right exam. It's been done before. You need a ruler, calculator, and you'll get given a periodic table. Read the instructions. A pencil. Try and get hold of a mechanical pencil. It works much better and you don't worry about sharpening it. Answer all the questions in the spaces provided. The marks for each question are shown in brackets. Look at it, highlight them. Make sure you read this carefully and tick each bit off when you've done it. Good luck! Question 1. A student investigated an aqueous solution of a salt. The student identified the salt solution contained only sodium ions and chloride ions. 1.1. Describe a test to identify sodium ions. Give the result of the test for 2 marks. You've got a space for the test and a space for the result. Now these are flame tests. Sodium gives a yellow flame, so in the flame test the result would be yellow. 1 mark for each. 1.2. Describe a test to identify chloride ions. Give the result of the test, 2 marks. Space for the test, space for the result. This is about acidified silver nitrate. So remember the analysis section. Acidified with dilute nitric acid, silver nitrate solution will give a positive white precipitate in the presence of chloride ions. 1 mark for each. Over the page, the student determined the concentration of sodium chloride in the salt solution. This is the method used. Weigh an empty evaporating basin dish. Add 25 cm³ of the salt solution. Heat the evaporating dish and contents. Weigh the evaporating dish and contents. Number 5, repeat steps 3 to 4 and until there's no further change in mass. And then number 6, repeat steps 1 to 5 3 more times. So 1.3. Why did the student heat the evaporating dish and contents until the mass did not change? So let's have a look at the method. We're heating and we're evaporating. So we need a dry dish. So we need to make sure that all the water from the solution has evaporated. 1 mark. 1.4. How did the student calculate the mass of solid sodium chloride remaining after steps 1 to 5? Tick 1 box for 1 mark. So let's look at the 4 choices. Number 1, the mass of 25 cm³ of salt solution plus the mass of empty evaporating dish. Number 2, mass of 25 cm³ salt solution minus mass of empty dish. Number 3, mass of evaporating dish and dry contents plus mass of empty dish. And the 4th one, mass of evaporating dish and dry contents minus mass of empty dish. So let's go up and have a look at what we have got here. We've already said that the evaporating dish needs to be dry. Okay, so we need then to not have any liquid present. So the solution, the first two, the two with solutions in, they can't be right. So let's look at our evaporating dish. Inside that dish, we've got our salt, and that is what we're trying to measure. So we need to take away the mass of the dish away from the mass of the dish and the salt. So it can't be number 3. It must be choice number 4. Mass of evaporating dish and dry contents minus mass of empty evaporating dish. Over the page, the student calculated the concentration of sodium chloride in the salt solution. Table 1 shows the results. So you've got the concentration of sodium chloride in grams per decimeter cubed, and you've got 4 readings. The percentage by mass of sodium ions in the sodium chloride is 39.3%. Calculate the mean concentration of sodium ions in the salt solution, and this is for 4 marks. There are 2 steps to this. The first step is to calculate the mean concentration of the sodium chloride. So we do that by adding the 4 trials together and dividing by 4. The mean concentration of sodium chloride is 35.2 plus 34.6 plus 36.4 plus 33.8 divided by 4 comes out at 35.0. Step 2 is to use the percentage by mass of sodium ions, which is 39.3%. So in sodium chloride, 39.3% of it is sodium ions, and the of it is the 35. So we're going to work out 39.5% of 35. And we mean concentration of sodium plus ions, Na plus, is 39.3 divided by 100 multiplied by 35. On your calculator, that comes out at 13.755, rounding up, mean concentration 13.8. So, for mark allocation, we get 1 mark for the mean sum and then 1 mark for the mean concentration, 35.0. We get 1 mark for the mean concentration of Na plus ions and 1 mark for the final answer, 4 marks. Over the page to question 2. This question is about ammonia and nitric acid. In the Haber process, ammonia is produced from nitrogen and hydrogen. Figure 1 represents the Haber process. Here's figure 1. You've got some nitrogen gas and some hydrogen gas going into a reactor. That feeds into a condenser. Then you've got pipe P, which is going from the condenser back into the reactor. 2.1. Pipe P links the condenser to the reactor. Why is the condenser linked to the reactor? Use figure 1 for 1 mark. So let's look at figure 1. We've got this condenser here where the ammonia gas is converted into liquid ammonia, and from the reactor there could well be unreacted nitrogen and hydrogen. And it's important to recycle this back into the reactor. So, to claim our 1 mark, recycle any unreacted hydrogen and nitrogen back into the reactor. 2.2. Which metal is used as a catalyst in this reaction? This is a simple recall. You've got to learn your stuff on the Haber process, and the catalyst is iron, Fe. Next page. Nitric acid is produced by reacting ammonia with oxygen. The word equation for nitric acid is ammonia plus oxygen gives water plus nitric acid. Platinum is a catalyst in this reaction. 2.3. Describe the test for oxygen gas. Give the result if oxygen gas is present. You've got your space for your test and result. 2 marks. This is all about glowing splint. You insert a glowing splint into the gas, and if it's oxygen, that glowing splint is rekindled or relit. 1 mark for each, 2 marks. Figure 2 represents the reaction profile of the catalyzed reaction between ammonia and oxygen. Here's figure 2. You've seen many of these before in most exams. 2.4. Complete the reaction profile for the catalyzed reaction in figure 2. You should label the activation energy and label the reactants and products using the names of the reactants and products. Activation energy, that is the distance of the peak of the line from the level with the reactant line. If we go up into the question, there's something here that will help us. There's the word equation, and the ammonia and the oxygen, they're the reactants. The water and the nitric acid, they're the products. So we simply copy those onto the profile. Remember, reactants go on the left, so ammonia plus oxygen. Products go on the right, nitric acid and water. So we'll get a mark for labelling the activation energy correctly, and we get a mark each for the reactants and products labelled correctly. 2.5. How would figure 2 be different if no catalyst was used? Tick 1 box for a 1 mark. The final energy level will be higher, the final energy level will be lower, the line would reach a higher peak, the line would reach a lower peak. What do we know about a catalyst? A catalyst lowers the activation energy. So, if there was no catalyst, the activation energy, the peak, would be higher. So if we look at our choices, the third choice is the one we should tick. The line would reach a higher peak, 1 mark. 2.6. Ammonia and nitric acid react to produce the salt ammonium nitrate. Ammonium ions and nitrate ions both contain nitrogen. Suggest one use of ammonium nitrate for 1 mark. Anything that's got nitrogen in it, and you should know this is a simple recall, and the answer is it's used in fertilizer, the manufacture of fertilizers. 1 mark. Over the page, 3.1. Hydrogen gas reacts with oxygen gas to produce water. Water is decomposed into oxygen gas using electricity. Which two words describe the reaction between hydrogen gas and oxygen gas? Tick 2 boxes for 2 marks. This one says alloying. It can't be alloying, that's to do with metals. Combustion, yes, that could be an answer there. Hydrogen burning in oxygen is combustion. Corrosion, no, that's to do with iron rusting. Endothermic, that means energy is put in. Well, when hydrogen reacts with oxygen, it produces energy. It's exothermic. So it must be the fifth one, reversible. And if you look above, you can see that the reaction is reversible. Hydrogen gas reacts with oxygen to make water, and water can be decomposed with electricity. So to get 2 marks, tick combustion and reversible. 3.2. Water molecules break down into hydrogen ions and hydroxide ions. The equation for the reaction is, which sentence describes this reaction at equilibrium? Tick 1 box for 1 mark. Water molecules break down at a higher rate than they reform. Water molecules break down and reform at the same rate. Water molecules break down at a lower rate than they reform. This question is asking you, what do you know about equilibrium? And at an equilibrium, the forward and reverse reactions occur at the same rate. So it must be the second box. Water molecules break down and reform at the same rate. 1 mark. 3.2 over the page. Water collected from rivers is used in the home for drinking and flushing toilets. Water used in the home must be potable. Potable water is safe to drink. Wastewater produced after use in the home is called sewage. Figure 3 shows how water is collected from rivers and returned to rivers after use. So here's figure 3. We've got the use in the home, and then the sewage going through process B through grids, effluent sludge. This effluent can go into the river then when it's treated, and we get this thing called groundwater, and then in process A we're producing potable water which goes to the home. Explain what happens to water in process A and in process B in figure 3. Do not refer to the use of water in the home. And this is a 6-mark question. Now this is a levelled response. So we look at this again. Let's have a look what it means. Level 3 is 5 to 6 marks. Relevant points, reasons, causes identified, given in detail, and logically linked to form a clear account. So let's look at process A. In process A, what we might call fresh water, which is groundwater, reservoirs, rivers, is filtered to remove any solids, and then it's sterilised with something like chlorine or ozone or UV light, which will kill any microbes or bacteria. Well, let's get that down on our response page. In order to produce potable water, fresh water, groundwater, reservoir, river water is first filtered to remove solids. It is then sterilised with either chlorine, ozone or UV light in order to kill any microbes or bacteria. So let's look at process B, the treatment of sewage. Sewage goes through a process of screening where large objects like twigs, dead sheep, etc. are screened using a metal grid, and this then goes into what we call the sedimentation phase. The filtered product goes into sedimentation tanks, and then the sludge, the particles, solid particles, sink to the bottom, and the floating on top is what we call the effluent. The effluent then undergoes aerobic digestion, and the solid sludge is taken through a process called anaerobic digestion. So let's get this down to finish our response. In process B, wastewater is first screened to remove any solids, twigs, grit and other large objects using metal grids. It then goes through a process called sedimentation where it is allowed to stand in a settlement tank. The heavier solids sink to the bottom and produce a sludge. The liquid on top, effluent, is then treated using aerobic digestion where bacteria break down organic matter. The sludge is treated by anaerobic digestion. 6 marks. Back of the net. Over the page, question 4. A student investigated an orange dye, A, using paper chromatography. Figure 4 shows the results of experiment 1 and experiment 2 using orange dye A. And you can see you've got two almost identical experiments. The only difference is on the right hand one there is ethanol, experiment 2 and experiment 1 there is water. 4.1. Explain why the yellow dye and the red dye travel different distances in experiment 1. Refer to forces of attraction between the dyes and the chromatography paper in your answer. And I've told you to do that, so make sure you do it. This is for 2 marks. The filter paper, we call that the stationary phase, and the solvent, the water, is called the mobile phase. And you'll see that the yellow dye has moved further than the red dye. The yellow spot is higher up than the red spot. Now the yellow spot has done this because it is more mobile. It has got less attraction to the filter paper. The red dye has greater attraction towards stationary phase. If we put this into a couple of sentences that's going to get us the marks. The yellow dye travels further because, remember it's an explain, because there is a weaker attraction between the dye and paper. So the dye will be carried further up the paper. 1 mark for the yellow dye travelling further, 1 mark for the weaker attraction. 2 marks. Over the page, 4.2. The student used the same type of chromatography paper in experiment 1 and 2. Explain why the yellow dye is in different positions in experiment 1 and experiment 2. Use figure 4, and this is for 3 marks. So this has got to be about the solvent. The only difference between the 2 experiments is the solvent. The experiment 1 has water, 2 ethanol. Notice the yellow dye in experiment 2 travels further than the yellow dye on 1. But let's write this out for our 3 marks. In experiment 2, the yellow dye travels further because the solvents are different. The yellow dye is more soluble in ethanol and therefore travels further. 1 mark for saying in experiment 2 the yellow dye travels further, 1 mark because the solvents are different, and 1 mark for the yellow dye being more soluble in ethanol. 3 marks. Figure 4 is repeated below. Figure 4 shows the results of experiment 1 and experiment 2 using orange dye A. Student investigated a different orange dye B. Figure 5 shows the results of experiment 3 using orange dye B. Notice there's only 1 spot. Question 4.3. Compare the purity of the orange dyes A and B. Give reasons for your answer and use figures 4 and 5 for 2 marks. As we've said, if we look back at figure 5, there's only 1 spot. This means orange dye B must be a pure substance. It hasn't separated into 2 or more substances. Whereas orange dye A has, you can see you've got your yellow and red spots. 2 spots on of dye A indicates that it is impure, it's not pure. So let's get this down. Dye A separates into 2 spots, so consists of 2 substances, therefore it's impure. Dye B has only 1 spot, and so it consists of only 1 substance. It's pure. 2 marks, 1 for each. 4.4. The student calculated that the RF value of the orange dye in the experiment shown in figure 5 was 0.48. Calculate the distance moved by the solvent front when the orange dye had moved 5.4 centimetres, and this is for 3 marks. Should record the RF formula. The RF is the retention factor is the distance travelled by the substance divided by the distance travelled by the solvent front. We're given the RF, that's 0.48. We're given the distance moved by the orange dye, the substance, that's 5.4 centimetres. Our challenge is to work out the distance moved by the solvent front, so we need to do a bit of rearranging of a formula. So divide both sides by RF, multiply both sides by the distance the solvent moves, and you end up with the distance the solvent moves equals the distance the substance moved divided by the RF. Now we can sub these numbers in. The distance equals the orange dye distance 5.4 divided by the RF 0.48. And when we crunch that on our calculator, we end up with 11.25. There's a mark for rearranging the formula, there's a mark for subbing in the numbers, and then a mark for the final answer of 11.25, 3 marks. Question 4.5. Why is the RF value of a dye not affected by how far the solvent front is allowed to travel? This is for 1 mark. Well, the RF value is a constant, so it's proportional to each distance. So if we can get this into a sentence, the ratio of the distance the spot moves to the distance the solvent moves is a fixed constant. In other words, the distance travelled by the spot is directly proportional to the distance travelled by the solvent. 1 mark. Over the page, 4.6. Another type of chromatography is called gas chromatography. Gas chromatography is an instrumental method of chemical analysis. Scientists tested the orange dyes using gas chromatography. Suggest 2 advantages of using the instrumental method of gas chromatography rather than paper chromatography. This is for 2 marks. This is a generic question and it comes up all the time. You just have to learn the standard answer for using instrumental methods. And you're talking about accuracy, we're talking about speed, and we're talking about resolution. So instruments provide greater accuracy, gets results faster, and greater resolution. Any 2 for 2 marks. Over the page, question 5. This question is about burning fuels in central heating boilers. In the future, gas central heating boilers may burn hydrogen rather than natural gas. Table 2 shows information about these fuels when 1 decimeter cubed of the fuel is burned in a central heating boiler. So here's table 2. We've got 2 columns for the fuel, hydrogen and natural gas. And then down the side, we've got the energy released, the mass of CO2, mass of water vapor, mass of oxides of nitrogen. And that's the important bit we'll come to in a minute. 5.1. Explain how oxides of nitrogen are produced when burning fuels. And this is for 2 marks. Under normal conditions and average temperatures, nitrogen will not combust with oxygen. However, at very high temperatures, it will. So the nitrogen from the air and the oxygen from the air will burn and produce what we call NOxes, oxides of nitrogen. So to get 2 marks, we must write in the space provided, oxides of nitrogen can be formed when nitrogen and oxygen from the air react at very high temperatures. So we're getting 1 mark for the nitrogen and oxygen from the air and 1 mark for very high or high temperatures. 2 marks. Over the page, question 5.2. Explain 1 positive impact of the environment on the environment of burning hydrogen rather than natural gas as a fuel. Use table 2 for 2 marks. So let's go up and have a look at table 2. What have we got here? Well, we've got the mass of CO2, and underneath the hydrogen column there is 0 grams of CO2. Under the natural gas, 1.8. So we know carbon dioxide contributes towards climate change, or we might call it global warming. So the natural gas when burned produces CO2, and CO2 contributes to climate change. We know that. Burning hydrogen produces no CO2, therefore it does not contribute towards climate change, or certainly reduces the effect of climate change. So in order to get 2 marks, we must write in the space provided, burning hydrogen produces no carbon dioxide. See table 2. Therefore, underlined because it's an explain. This will reduce the effects of climate change or global warming. 1 mark for producing no carbon dioxide, 1 mark for reducing climate change. 2 marks. 5.3. Explain 1 negative impact on the environment of burning hydrogen rather than natural gas as a fuel. Use Table 2. This is for 2 marks. So let's go back to Table 2 and look at the effects of burning hydrogen. You can see here on the bottom row, when we burn hydrogen, we're getting a greater mass of NOxes, nitrogen oxides. So therefore, we can put that into our answer. You will recall that more nitrogen oxide in the atmosphere can contribute towards acid rain, which is a negative effect. So, in order to get 2 marks for this question, you must write in the space provided. Table 2 shows an increase in oxides of nitrogen produced when hydrogen is burned. Oxides of nitrogen contribute to the increase in acid rain. So it's 1 mark for showing an increase in the oxides of nitrogen when nitrogen burns, and 1 mark for the mentioning of acid rain. 2 marks. Over the page for 5.4. Air is 20% oxygen. Calculate the volume of air needed to provide enough oxygen to react with 3.50 decimeters cubed of hydrogen gas. The equation for the reaction is 2H2 plus O2 goes to 2H2O, and it's for 3 marks. Now, the key fact in this calculation is that 1 mole of any gas occupies the same volume at room temperature and pressure. So there's no need to do any calculations for moles, and there's no relative atomic masses required. From the equation, the mole ratio says 2 moles of hydrogen react with 1 mole of oxygen. Therefore, 3.5 decimeters cubed hydrogen will react with 3.5 divided by 2 decimeters cubed oxygen due to the 2-to-1 ratio. That equates to 1.75 decimeters cubed. At the top of the question, air is 20% oxygen. So when we burn hydrogen in air, 20% of oxygen in air equates to 1/5. In order to get the correct volume of oxygen, we need to provide 5 times the volume of air. So in other words, we need 1.75 multiplied by 5, because only 1/5 of the air is oxygen. So the volume of air required is 1.75 multiplied by 5, which equals 8.75 decimeters cubed. So it's 1 mark for working out the volume of oxygen from the mole ratio, 1 mark for the multiplication of that volume by 5, and 1 mark for the final answer of 8.75, 3 marks. 5.5. Central heating boilers can also burn kerosene. Kerosene is produced from crude oil in a fractionating column using fractional distillation. In the first step, crude oil is heated and hydrocarbon vapours are formed. Explain how kerosene is produced from these hydrocarbon vapours, and this is for 3 marks. So let's take a look at this image from of a fractionating tower or column, and you'll notice that the fractionating column is hot at the bottom and cool at the top. So as the vapours rise up the column, they get cooler and cooler. And you'll also notice that there are vents at the side where different fractions come out, and the reason that they come out where they do is because they condense. So our kerosene vapours will condense, and each of these fractions condenses at a different boiling point. So the reason kerosene vapours condense is because they condense at their boiling point. So in order to get 3 marks for this question, we're going to write in a fractionating column, the temperature gets cooler as the vapours rise up the column. The kerosene vapours condense at their boiling points. So to get our marks, we must have a mark for saying that the column is cooler at the top, and a mark for condense, and a mark for boiling point. 3 marks. Over the page, question 6. This question is about materials used to make bicycles. Figure 6 shows a bicycle, and it's pointing to the chain and the frame. Table 3 shows information about 2 materials used to make bicycle frames. So, on one side and one column you've got aluminium alloy, in the other column bamboo. Then different categories, you've got raw material down the left hand side, the cost of the frame in pounds, strength in arbitrary units, the mass of the frame in kilograms, the lifespan in years, and one method of disposal at the end of life. Next page, question 6.1 says, evaluate the use of aluminium alloy and of bamboo for making bicycle frames. Use table 3, and this is for 6 marks. And don't forget, wherever you see the word evaluate, you must make a choice between the things on offer. So you've got to choose between bamboo or aluminium alloy. Now, because it's a levelled mark response, here we are, look, level 3, a judgment, I've highlighted it there, strongly linked and logically supported by a sufficient range of correct reasons. Now, this type of question requires you to make a plan. You can't really tackle this without planning. Now, you can use the additional pages at the back of the booklet. Just draw 2 columns, jot down the key points, then cross it out when you've written your answer. Some of your points will come straight from the table and some will be your own knowledge. So, aluminium is a finite resource and clearly bamboo is renewable. Aluminium ore is mined, so there is polluting in mining, and in growing bamboo we use land which could have grown food on. We can see aluminium is low cost, so the frames can be replaced more frequently. It's also stronger, which means a harder ride. Bamboo is more absorbent to shock, and therefore it's a smoother ride. Aluminium is a low density, so you get a more efficient power transfer. This means it's just basically to pedal. It's easier to pedal. It's a lot easier to carry around. You can carry it a lot easier if it's lighter. Bamboo frame lasts longer, but it does need treatment and can be affected by weather like rain. Okay, now disposing of it, aluminium is recyclable, but you can use bamboo and burn it to get energy to create electricity. So therefore, bamboo is also carbon neutral. Because aluminium forms its own oxide layer, therefore protecting it, there is no corrosion. And it's widely available. There's tons and tons of aluminium ore in the world, whereas bamboo is more difficult to source. The good thing is neither of these 2 materials will go into landfill. Let's try and put this in a response that's going to get us our 6 marks. Aluminium ore is a finite resource, whereas bamboo is renewable. Mining aluminium is polluting, and growing bamboo can take up land needed for food production. The low cost of aluminium means it does not need replacing as often. Aluminium is stronger but stiffer, so frames are more robust, but the ride is bumpy. Bamboo's flexibility affords a more comfortable ride. Aluminium is less dense, so allows more efficient power transfer and is easier to transport. Bamboo frames last longer, so need to be replaced less frequently. Disposal, aluminium can be recycled, whereas bamboo can be burnt to produce energy, so is more carbon neutral. Aluminium is resistant to corrosion, whereas bamboo needs treating to avoid water absorbance. Neither require landfill. Now, this is the bit where sometimes I suggest that you keep one of your factors above and say, I believe that X or Y is a superior material because la-da-da-da, and that would be a way of getting your final mark for your evaluation. 6 marks. 6.2. Explain why aluminium alloy bicycle frames do not need protection from corrosion. This is for 2 marks. You will recall that aluminium quickly forms an oxide layer. Aluminium is quite a reactive metal. So it forms this oxide layer, which is very similar looking to aluminium itself. And this oxide layer provides protection against attack from things like water, oxygen, etc. So to get 2 marks, we must write, in the alloy, aluminium forms an oxide layer on its surface. This forms a barrier and prevents elements and other things like water, air, etc. coming into contact with the aluminium. 1 mark for the oxide layer and 1 mark for prevention of contact with water, etc. Over the page, 6.3. Bicycle chains are made from an alloy of iron. Bicycle chains rust without protection. Paint is not used to protect bicycle chains from rusting. Suggest how bicycle chains can be protected from rusting for 1 mark. If you have a bicycle, you will know that you have to keep the chain oiled or you have to apply grease. 1 mark. 6.4. Bicycle frames can be made from a composite of carbon fibres embedded in a polymer resin. What description is given to this composite, to the carbon fibre component and to the polymer resin component, for 2 marks? If we look at these notes here, most composites are made of 2 material: a matrix or binder surrounding and binding together fibres or fragments, and this is called the reinforcement. Our carbon fibre would be our reinforcement, and the polymer resin would be the matrix or the binder. 1 mark for each, 2 marks. Over the page, question 7. This question is about sulfuric acid. Question 7.1. Sulfuric acid contains sulfate ions. Describe the test for the presence of sulfate ions in sulfuric acid. Give the result of the test for 2 marks. We have a space to write the test and then a space to write the result. This is a simple recall of your analysis topic. The test for sulfate ions is barium chloride, in which you get a white precipitate. So, in the space provided, you'd write add barium chloride solution to the acid for the test, and for the 2nd mark, the result is a white precipitate indicates the presence of sulfate ions. 2 marks. One stage in the industrial production of sulfuric acid is the reaction of sulfur dioxide with oxygen to produce sulfur trioxide. This reversible reaction reaches dynamic equilibrium. Figure 7 shows the percentage yield of sulfur trioxide in this reaction at different temperatures. So here's figure 7. We've got the percentage yield up the y-axis, and along the x-axis we've got the temperature in degrees Celsius. 7.2. Which statement about the forward reaction is correct? Use figure 7 and tick 1 box for 1 mark. So the yield is greater at high temperatures because the reaction is exothermic. The yield is greater at high temperatures because the reaction is endothermic. The yield is smaller at high temperatures because the reaction is exothermic. Finally, the yield is smaller at higher temperatures because the reaction is endothermic. We'll do as we're told. We'll look up at figure 7, and we can see here that we've got a high yield, but the temperature is lower. It's round about 350 compared to high 800 down at 30%. So if we look at our theories on the position of equilibrium and regarding temperature change, if the temperature is increased, the equilibrium will always move in the endothermic direction. So if the temperature is increased, the yield from the endothermic reaction increases and the yield from the exothermic reaction decreases. Back to the choices. The yield is greater at high temperature because it's exothermic. That can't be correct. Yield is greater at high temp because it's endo. That's not correct. Yield is smaller at high temperatures because it's exothermic. Could be correct. Yield is smaller at high temperatures because the reaction is endo. No. So it's got to be choice number 3. The yield is smaller at higher temperatures because the reaction is exothermic. And that's a lot of effort for 1 mark, but they all count. The equation for the reaction is 2SO2 gaseous plus O2 gaseous in equilibrium with 2SO3 gaseous. 7.3. Explain why the percentage yield of sulfur trioxide in this reaction is greater if the pressure is higher, and this is for 2 marks. Let's look at the theory for change in pressure. In gaseous reactions, an increase in pressure, equilibrium will move towards the side of the reaction that has the least number of gaseous molecules. So look up at the equation. We've got 2 molecules of SO2, 1 of O2 and 2 of SO3. So we've got fewer molecules on the right hand side. Therefore, the equilibrium is going to move to the right hand side. Hence, we get a greater yield because more product is formed. So, to get our 2 marks in the space provided, there are fewer gaseous molecules on the right-hand side of the equation. Therefore, the equilibrium will shift right towards the products and a higher yield. 1 mark for the fewer molecules and 1 mark for the shift to the right. 2 marks. 7.4. In industry, the reaction is done at 450 degrees Celsius and atmospheric pressure. Under these conditions, the yield of sulfur trioxide is 86%. Suggest two reasons why higher pressure is not used for 2 marks. Whenever we have issues of high pressure, there is safety has to come into play. And also, to produce high pressure requires a lot of energy. Now, the yield is already good at 86%. In order to get 2 marks, we could have a list of 4 possible answers. Risk of explosion at higher pressure, cost of building stronger vessels, cost of additional energies not paid back, and the yield is already 86%. Any two for 2 marks. Over the page, 7.5. This reaction uses a catalyst to increase the rate of reaction. The catalyst is a metal oxide, which is the most likely metal in the metal oxide catalyst. Periodic table and tick one box. So you've got a choice of 4: aluminium, barium, potassium, and vanadium. What do we know about catalysts? Catalysts, metal catalysts or metal oxide catalysts. Whenever we think of metals and catalysts, we go straight to the transition metal block of the periodic table. So let's have a look at it now. Here's vanadium, smack there with the purple. So to get 1 mark for this question, we put a tick in the box vanadium. Over the page, question 8. This question is about monomers and polymers. Compound A has an alkene functional group and an ester functional group. Figure 8 represents a molecule of compound A, and you can see the molecule displayed there below. Here's your carbon-carbon double bond, and here's your ester link. Question 8.1. Draw a circle around the alkene functional group on figure 8 for 1 mark. And there's your carbon-carbon double bond for 1 mark. 8.2. Describe what will be seen when compound A is shaken with bromine water, and this is for 2 marks. This is your classic bromine water test for the double bond. It's a simple recall. The orange of the bromine water will turn colourless. You can say it's decolorized, but you must have orange and colourless or decolorized. So to claim 2 marks for this question, you must say orange of the bromine water will turn colourless or will be decolorized. 8.3. Figure 9 is a repeat of figure 8. Here's figure 9. Draw a circle around the ester functional group on figure 9. And this is just for 1 mark. So, what do we know about an ester? An ester is a carbon double bond oxygen, carbon single bond oxygen. So if we look up at the molecule there, we can see our carbon double bond and our carbon single bond oxygen. So that's our ester link for 1 mark. 8.4. Compound A has the formula C4H6O2. Compound A is flammable. Write a balanced equation for the complete combustion of compound A. And this is for 3 marks. Now, at first, this looks a very tricky question. If it's combustion, then it must be combining with oxygen. Looking at the formula of compound A, there's only carbon, hydrogen, and oxygen. So the products can only be carbon dioxide and water. So we know at normal conditions, oxygen is O2. So we can write in the compound A formula and O2, and then followed by your CO2 and H2O. I would urge you to use a pencil for this because you are going to be writing numbers in and then rubbing them out again when they don't fit. So let's look. If we look at the compound A, we've got 4 carbons there. So let's stick a 4 in front of CO2. And we've got 6 hydrogens. So let's stick a 3 in front of H2O. That gives you 6 hydrogens. So if we add up the oxygens, we've got 11 oxygens. So that's not going to fit. 4 on the left and we've got 11 on the right. There's no way we can balance those up. So let's rub them out and start again. And one of the easiest ways to solve this is to double up. So if we double up compound A, so we get 2 C4H6O2s and then go from there, see what we get. Now, if you've seen my revision video on balancing equations, it's best to write out the numbers of each atom in the molecule down underneath so you can keep check of them. So we've got 8 carbons, 12 hydrogens, 4 oxygens. So let's balance up the carbons first. So we've got 8 carbons in front of the CO2. Those 12 hydrogens on the left are going to give us 6 H2Os because 6 2s are 12. So the 6 in front of the H2O. Now, we've already got those 4 little oxygens, so we mustn't forget about those. On the right-hand side, we've got 16 oxygens in the carbon dioxide and 6 in the water. That makes 22. Take away those 4 from compound A, then we can balance up the O2. So 22 off, take away 4 is 18. So there we have to stick a 9 in front of the O2 to make that up to 18. Jobs are gone. Go back and double check that everything matches and everything balances, and that's the 3 mark. You really did earn those 3 marks, I have to say. Hey-ho, they all count. Over the page, 8.5. Many molecules of compound A join together to form polymer B. Complete the displayed formula equation which represents this reaction. Now, this question is for 2 marks. So, this looks a very complicated molecule, so let's get rid of a little bit of it just to make it easier. This bit looks more familiar to you from your work you've done in class. So first thing, that N in front of the molecule becomes the N at the bottom right outside the bracket. That double bond becomes a single bond between those 2 carbons. You can see why we got rid of all the bits on the left-hand side just to make it simpler. So 1 mark for the double bond going to a single bond, 1 mark for the N bottom right-hand corner, 2 marks. 8.6, what type of polymer is polymer B? Tick 1 box. Choices are addition polymer, condensation polymer, DNA, or protein. Let's go back to the previous question. We can see that N means a very large number of these monomers, and they join together or add on to each other. So if we go back to the question, this has to be an addition polymer. This has to be addition polymer, so tick the box addition polymer for 1 mark. Over the page, 8.7. Polymer B is a polymer which melts when heated. What word is used to describe polymers which melt when heated for 1 mark? It's a simple recall. When something melts, it goes soft. That's the clue. So this is a thermosoftening polymer. Okay, thermosoftening, 1 mark. 8.8. Explain why some polymers do not melt when heated, and this is for 2 marks. This is all about cross-links. If you look below at the diagram, the ziggy-zaggy lines represent 2 polymer chains, and those polymer chains have covalent bonds between them, which are very, very strong and cannot be broken. So, in order to get 2 marks for this question, you must write in the space provided there are cross-links between the polymer chains. Therefore, too much energy is required to overcome these cross-links. 2 marks. Over the page, question 9. A student investigated the rate of the reaction between zinc and sulfuric acid. The equation for the reaction is Zn solid plus H2SO4 aqueous goes to ZnSO4 aqueous plus H2. Figure 10 shows the apparatus. And here's figure 10. So you've got your sulfuric acid and your zinc in a conical flask. You've got a stopper with a delivery tube delivering a gas into a 50 cm cube measuring cylinder. This is the method used. Pour 50 cm cubed of sulfuric acid into the conical flask. 2. Add excess zinc to the conical flask. 3. Insert the stopper and start a timer. 4. Measure the volume of hydrogen collected in the 50 cm cubed measuring cylinder every 20 seconds for 180 seconds. 9.1. Explain why the volume of hydrogen collected in the 50 cm cube measuring cylinder is less than the volume of hydrogen produced, and this is for 2 marks. Let's go back up to the diagram. Look at what the method said. We've got a stopper, so we're putting zinc in. Then as soon as we put that zinc into the acid, we've got to quickly get the stopper on. So some of the gas will escape. So the container, the flask and the tube is full of air. So that air will go into the measuring cylinder first before the hydrogen. So there'll be less hydrogen. So in order to get 2 marks, you must write in the space provided the stopper is removed to add the zinc. As soon as the acid is in contact with zinc, hydrogen is produced and will escape before the stopper can be replaced. Now, there is another answer to this, and you probably realise this. The apparatus, the conical flask and delivery tube, are full of air. And when the hydrogen is produced, the air has to be pushed out, and the only place it can go is into the measuring cylinder. So the first few centimetres cubed of the measuring cylinder will be air and not hydrogen. Over the page, figure 11 shows the volumes of hydrogen collected in the 50 cm3 measuring cylinder after 40 seconds and after 100 seconds, and here's figure 11. 9.2. Determine the number of moles of hydrogen collected between 40 seconds and 100 seconds. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed. Now this is for 4 marks. The first thing we have to do is work out how much gas, what volume of gas has been produced between 40 and 100 seconds. So we must read the readings on the 2 measuring cylinders. So 100 seconds, there are 39 cubic centimetres of gas produced, and after 40 seconds, 25. So the volume of gas produced between 40 and 100 must be 39 take away 25, which is 14 cubic centimetres of gas. Now we can use the statement there. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed. We have to work out what fraction of 24 decimeters cubed is 14 centimeters cubed. So we convert 14 cubic centimeters into decimeters by dividing by 1,000. And that equals 0.014 decimeters cubed. So the number of moles of hydrogen collected is 0.014 divided by 24 decimeters cubed. So when you crunch that on your calculator, you get 0.00058, or in standard form, 5.8 times 10 to the minus 4. Let's look at mark allocation. We're going to get 1 mark for working out the volume of gas produced. We're going to get another mark for converting it to decimeters cubed. Third mark is for the fraction of 0.014 divided by 24, and 1 mark for the final answer, 4 marks. Over the page, a different student investigated how the concentration of sulfuric acid affected the rate of the reaction. 9.3. The student did a different experiment using sulfuric acid of a concentration of 0.40 moles per decimeter cubed. The student calculated the number of moles of hydrogen collected after every 20 seconds. Figure 12 shows the results. And here's figure 12, it's a graph. Time on the x-axis and the moles of hydrogen collected upon the y-axis. The page to the question, determine the rate of reaction at 45 seconds. You should draw a tangent on figure 12. Give your answer in standard form. So let's flip back to figure 12. This is a 5-mark question. Let's look at the graph. What we need to do is find out where 45 seconds are. So halfway between 0 and 50 is 25. Each one of those little marks is 5, so 45 is there. And we just draw a construction line up to the curve, so that's where we're going to draw our tangent, okay, at that point there, just there. So we're going to put our ruler across here to get our tangent. So here's a ruler, we draw a tangent, a nice straight line with our ruler and pencil. And now we've got to work out the gradient of this tangent. So again, we need further construction lines. And we're going to draw those, we'll do those in black now. So there's one from the top there at 0.18, one across just under 0.010. So we're going to work out the values of the x and the y. So the x is quite simple, straight down to there. We've already worked out what those mean. That's halfway, 75, 80, 85, 95 on the x, and it starts at 0, so x is 95 seconds. Now the y starts here, so this is 0.08. Each one of those is 0.0004, so that's 84. Add it all up, that comes to 0.0096. I've missed a zero out, but hey ho. So across the top it's 0.018, so the y is 0.0018. Take away 0.0096. Crunch that on your calculator, and what you get is 0.0084. So the rate of the reaction is equal to the gradient, which is y divided by x. So we go back up and sub in the numbers. Y 0.0084, x 95 seconds. Back to the paper. There's our sum, 0.0084 divided by 95 equals 0.00008421. Converting that to standard form, we're looking at how many decimal points do we move to the right. It's 5. So that ends up 8.4. We're going to go 2 sig figs, 8.4 times 10 to the minus 5. And that's our final answer. Now, allocation of marks. 1 mark for the tangent. 1 mark for working out x and y, 1 mark for the sum at 0.0084 over 95, 1 mark for the answer, and 1 final 5th mark for putting it into standard form. 5 marks back of the net, well earned. Over the page, 9.4. Figure 13 shows the results for a 0.40 moles per decimetre cube sulfuric acid. And here's figure 13, it's another graph. The student repeated the experiment using 0.20 moles per decimetre cube sulfuric acid instead of 0.4. Excess zinc was used in each experiment. Sketch a line on figure 13 to show the results that you would expect. And this is for 2 marks. So if you look at the concentration, it's gone from 0.4 to 0.2. So the concentration has halved. So there's half the number of hydrogen ions to react with the zinc. So 2 things are going to happen here. It's not going to be as rapid, it's not going to be as fast a rate because the 0.2 is less concentrated, and there should be half the amount of gas produced. As a result, the line will be less steep and will go across and flatten at half the value on the current graph. So it flattens at 0.0168. Divide that by 2, it will flatten now at 0.0084, which we've indicated here with the red construction line. So all we need to do is draw a less steep line, levelling off, level with our red construction line. 1 mark for the less steep line and 1 mark for levelling off at half the original. 2 marks. Over the page for the last question. Hurrah! 9.5. Explain how increasing the temperature would affect the rate of reaction between zinc and sulfuric acid for 3 marks. This is a bog standard. You should have learnt this in your lessons in chemistry. This is all about collision theory. If we increase the temperature, the particles have more energy. If we increase the temperature, the particles have more speed. So their energy and their speed, their kinetic energy, is higher, greater. And there will be more frequent and more energetic collisions. This will mean more successful collisions, and therefore the rate of the reaction will increase. So, to get you 3 marks, increasing the temperature increases the energy and the speed of the particles. This means that there will be more frequent and more energetic collisions. Here's the explain. Therefore, there will be more successful collisions, which increases the rate of the reaction. So, we're going to get 1 mark for the increase in the energy and speed, 1 mark for more frequent energetic collisions, and 1 mark for more successful collisions causing an increase in the rate of reaction. 3 marks. End of questions. So if you've got this far, you know what to do. Give us a like, subscribe to the channel, have a look at some of the other videos in the playlist. That's me saying goodbye, see you soon, bye.